It's my pleasure to introduce Professor Gilles Brassard. Professor Gilles Brassard received a master's degree in 1975, his PhD in computer science from Cornell University in 1979, working in the field of cryptography. He has been a faculty member of the University of Montreal, where he became full professor in 1988 and was given a Canada Research Chair in 2001. Professor Brassard is well known for his fundamental work in quantum cryptography, quantum teleportation, quantum entanglement distillation, quantum pseudo-telepathy, and the classical simulation of quantum entanglement. In 1984, together with Charles Bennett, he invented the BB-84 protocol for quantum cryptography. He later extended this work to include the cascade error correction protocol, which performs efficient detection and correction of noise caused by eavesdropping on quantum cryptographic signals. He has won numerous awards and honors, including Marie Victorian, the highest scientific award of the Government of Quebec in 2000, Gerhard Herzberg Canada Gold Medal, Canada's highest scientific honor in 2009, and Killam Prize for National Sciences in 2011. His aim is to continue pushing the frontiers of knowledge by investigating novel uses of quantum mechanics for the enhancement of our information processing capabilities, covering the whole range of research from pure theory to actual experiments. I invite Professor Gilles Brassard.
For the invitation. In this talk, I'm going to give an overview, non-technical overview of quantum cryptography, and starting from first principles and move on to perspective for the future. But first, let me tell you a bit about classical cryptography. So let me first talk to you about classical cryptography. Cryptography as such is an art and science. It's been going on for at least 2,500 years old. We can even find one of the yogas in the Kama Sutra about cryptography. So it's really old. And essentially, it's all about a battle. And it's a battle between code makers and code breakers. And it looks like this. I'm going to introduce my two favorite characters, Alice and Bob. Alice and Bob want to communicate over an insecure channel, so the eavesdropper can overhear all that you're saying, but he would like still to communicate in private. So that's the purpose of cryptography, is for Alice and Bob to be able to encipher and decipher messages that only they can understand, because they have some secret that the eavesdropper does not have. And in good cryptographic practice, we assume that the secret that they have is just a key. It's not the method that they use. It's very important, if you want to be secure, that the method you use to encipher, decipher should be known to the enemy, or at least you should not assume it's unknown when you want to establish security. You have just some piece of information known as a key, which is your secret. And that it's fine to assume that the enemy does not know it. And of course, the question, since it's a battle really raging for millennia, so the question, of course, is who's going to win? And throughout history, it's at least up until about maybe 35 or 40 years ago, it's always been the code breakers that won the war. If you look throughout history, new codes or new ciphers have been invented, and they've always been broken. Sometimes it took a long time. For instance, a system known as le chiffre indéchiffrable, that's how it's called in English, not in French. It took 300 years before it was broken, but it was eventually. In fact, it was broken by no less than Charles Babbage, who is the inventor of the modern-day computer, sometimes before Turing. But still, the question is there. Who's going to win? And in fact, some people, like Edgar Allan Poe. Edgar Allan Poe is a very famous American novelist of the 19th century. And in his spare times, he was an enthusiastic code breaker. really as an amateur, he didn't have any formal training, but he was really good at breaking codes or ciphers. And he had a regular column in the local newspaper where he challenged readers to submit puzzles that he would break, and almost all the time he was able to break them. So Poe also was extremely influential in cryptography in kind of a strange way, not being a scientist, because he wrote, among his many short stories, he wrote one called The Gold Bug. And The Gold Bug is a story which is all centered around a cryptogram and how it's broken and what happens after that. And this story was a starting point for many really important cryptographers that came afterwards who got interested in cryptography because of this, because they read this story when they were children. Like William Friedman, for instance, the foremost American cryptographer and cryptanalyst of the first half of the 20th century, who invented the word cryptanalysis, by the way. All right, so Poe's, Edgar Allan Poe's conviction, what he thought is summarized in this quote of his, that human ingenuity cannot concoct a cipher which human ingenuity cannot resolve. Said plainly, code breakers will always win. And the whole purpose of this talk is to ask the question, was he right? All right, so now let's move on to quantum mechanics. My story, if we forget about Poe and the previous 2,500 years old, 2,500 years of history, my story really begins with this man, Stephen Wiesner. And Stephen Wiesner, in 1970, wrote an extremely important paper, conjugate coding. Well, that's the first page, or the title page is like this. So conjugate coding was written in 1970. Took a long time before it got published, and I'll tell you why in a minute. But in that paper, Wiesner, to the best of my knowledge, was the first person ever to think of using quantum mechanics to achieve information processing purposes that are classically impossible. Now let me explain what I mean by this. In his abstract is right here. So what he has here is that he proposes to use the uncertainty principle, as in Heisenberg stuff, the uncertainty principle to achieve novel forms of coding. And what he meant by novel forms is that, so what I mean by novel forms, or what he meant, again, is that we want here to do things which are classically impossible. Now, of course, quantum mechanics had been used at 1970, had been used for years before that for information processing purposes, because a transistor is a quantum mechanical creature. Without understanding quantum mechanics, there would be no transistor, or before that, the vacuum tube or the valve. However, what the transistor allows us to do is to compute much faster than with a cog and wheel machine or an abacus. We only go faster. We cannot do anything more if we have enough time or enough memory. We can only do it faster having an electronic computer than classical than Babbage's cog and wheel machine. Whereas what Wiesner is talking about here is to do things which are just impossible in the classical world. And that's what I think is most interesting about quantum information from a computer science perspective. So specifically, this is page 1 of his paper. In page 1, he says, we will first give two concrete examples of conjugate coding. Example 1 is a means for transmitting two messages, either but not both of which may be received. So what he meant there, remember, 1970, if you're a computer scientist or a cryptographer, this will ring a bell to you. So in 1970, Wiesner had this idea that because quantum information, if you want to measure it, that is, any measurement process on quantum information is destructive and only gives you partial information. Then it's possible, perhaps, he had the idea that perhaps it would be possible, using quantum information, for Alice to take two classical messages, encode them both in the same quantum signal, send the quantum signal to Bob, and then Bob would have a choice, his own choice, of one of two possible measurements, one measurement of the quantum signal sent by Alice would reveal the first message, but would destroy the other, and vice versa. The other measurement that Bob could do on the quantum signal would reveal the second message. But you see, because quantum measurements is destructive, either one measurement that Bob would make would destroy the other message. So that Bob could choose which message to read, Alice would never know which Bob has chosen. So Alice would not know which it is, but Bob could choose whichever one he wanted to read, but whichever he reads, he would only be able to read that one and not the other. This became known in computer science and cryptography about 15 years later as 1 out of 2 oblivious transfer. But that was really invented as a notion by a physicist, Stephen Wiesner. The second example in Wiesner's paper, example 2, for some reason example 2 is much better known. So the second idea of Wiesner was to use quantum information to produce money, banknotes, that would be physically impossible to counterfeit. And here the idea is extremely simple. The idea how to do the thing I mentioned before, this sending 2 messages into one, this is not all that simple. But example 2 is extremely simple, even simple-minded, and that's what I like about it. Essentially, because quantum information cannot be measured, and more to the point, cannot be copied, you cannot clone quantum information. Well, if you put quantum information on a banknote, this is an artist's impression, of course, in which we represent quantum information by single polarized photons that are kept on the banknote somehow. Don't ask how. Just, I mean, we're not asking. This is not meant to be practical. It is just in principle idea. So if you could keep quantum information on your banknote, then because quantum information cannot be copied, well, then the banknote cannot be copied. As simple as that. Now, of course, if you want that to be in any way practical, if you want it to be interesting, forget about practical, then it must be possible for someone to verify the validity of the banknote. Because if you cannot make copies, but nobody can tell if it's valid anyways, well, then you could make fake copies, and still people couldn't tell it's not valid. So it would be completely useless. So Wiesner's idea was to have a classical serial number, and from the serial number, there'd be a big book that would say what checks to make on the banknote to verify validity. And anybody who would have this book could make fake banknotes, could produce these banknotes. So this book had to be kept very secret. So in other words, you needed the same secret book to be able to manufacture the banknotes or to verify their validity. And that made it somewhat not very practical because the only thing you could do with these banknotes really, you could go to your bank, which has the book to make them or verify them. You could go to the bank, withdraw a banknote, so take the money out of your bank account and leave the bank with your banknote that you put in your truck. And then you could drive around town with your banknote, but you could not spend it anywhere because nobody could verify validity along the way. And then all you could do with it is come back to the same bank and deposit it back. Or maybe some other branch of the bank that has the same secret book. So not very useful. Nevertheless, this crazy idea was the starting point of the entire field of quantum cryptography, and to a lesser extent of quantum information science. Lesser extent because quantum information science would have sprung up independently of this in the form of Feynman and David Deutsch quantum computing. But anyways, now the beautiful thing is that this crazy idea, even though it's completely impractical, what happened is that Wiesner submitted it to the IEEE Transactions on Information Theory. Now, Wiesner is a physicist. He wrote a paper as a physicist using physics jargon, perfectly fine, but he submitted to an engineering journal. So, of course, neither the editor nor any of the referees had any clue what he was talking about. And the paper was rejected. And 1970 again. The paper was rejected, and the story could have died there. Because Wiesner didn't really do very much about it afterwards, except one thing, which is to talk to his best friend, Charles Bennett. Now, Wiesner and Bennett, at the time, well, previously, they had gone to undergraduate college in the same university. And now they had moved apart. They were doing their PhD in different places, but they kept visiting each other. And Bennett, So Wiesner told Bennett about his idea. And that's about all he did with it, other than submitting and being rejected. And unfortunately, Bennett did talk about it to other people. And at some point, Bennett mentioned the idea to me, and that's when I met him for the first time in 1979, so that's almost 10 years later. And when Bennett told me about this idea of this banknote, at that time, I just finished my PhD on classical cryptography. And so I had all this other bag of tools of classical cryptography, which I immediately thought of a way of improving the Wiesner banknote by making it possible to verify validity by someone who does not know how to make one. So I thought of the idea using the then new notion of public key cryptography, of a way by which anybody could verify validity of one of these banknotes. But still, you needed a secret to manufacture new ones. Now, this was only computationally secure, but still, it made the thing somewhat more interesting, and that's how we got our first paper, which appeared in the proceedings of the Crypto 82 conference. That's the first page, and I'm only showing you this first page because this is the first time that the words quantum cryptography came out in print, 1982. Now, so these improved banknotes, as I just told you, were only computationally secure, but this idea has been worked on by many people afterwards, and the latest paper called Quantum Money, it will come out, it's not out yet, but it will come out in the communications of the ACM in a few months, I suppose. And that gives a good history of the entire field, and also more interesting ways of implementing these banknotes. So this is not yet out. But all this being said, I think, well, these quantum banknotes, well, it's interesting, I think. But is it really cryptography? Right? I mean, it's somehow, yes, perhaps, but it's not this. It's not sending confidential messages. So the next thing that happened is that Charlie Bennett and I, we were thinking about these ideas, and we realized that these banknotes, well, they're fun perhaps, but they're really impractical because you need to store quantum information for a macroscopic amount of time, which back then was just not at all feasible. It's not so much feasible today either. So these banknotes were not really practical, and then we kind of realized something obvious, which is that photons, which was the carrier of quantum information we were thinking of at the time, we were not thinking about ion traps or neutral atoms or any of these things that in those days. We were only thinking about photon polarization for carrying quantum information. And then we realized that that of course photons had been created to communicate information, not to store it. Photons like to travel, of course, although not quite as fast as neutrinos, but still they're pretty good at that. And so that's when we had the next idea, which was to use quantum information to send confidential messages. So to do kind of main core cryptography. But then what we wanted to do was do something different, something that classical cryptography cannot do. Essentially, our goal was to obtain unconditional security. Now, what I mean by unconditional security is that Alice could send a message to Bob in such a way that an eavesdropper would not be able to know what the information is, would not be able to read the message, would not even be able to obtain partial information about it. And this, regardless to his computing power and his technology. So by unconditional, we mean, in fact, three things. We mean no information obtained by the eavesdropper. We mean that this applies even if the eavesdropper has unlimited power, or rather power limited only by the laws of physics. So unlimited technology and unlimited computing power and technology limited only by the laws of physics. And the third thing we mean here is that, furthermore, we could prove it. We could have a complete formal mathematical proof of security under the smallest possible assumptions. In this case, the assumption would be that quantum physics is correct. We need something, of course, and we can never prove that quantum physics or any other quantum physical theory is correct. But under that assumption, we wanted a complete mathematical proof of security, of unconditional security. So, it turns out, in fact, that unconditionally secure cryptography has been around for more than 100 years. In the classical world, there is a very well-known, very simple way to achieve unconditional security. It's known as a one-time pad. I'm not going to explain it, but it's very simple. And the one-time pad gives provable unconditional security, or at least for confidentiality, I should say. But it requires a very large amount of key material, meaning that Alice has to let's say, produce a long random bit string, for instance, or a long key. And somehow she has to transmit that key over to Bob, so that Alice and Bob would have the key in common, a very long key, and that would be unknown to an eavesdropper. But once they've succeeded in doing that, if Alice and Bob are able to have a very long secret key, then they're in business. Then using that, they can transmit in a purely classical fashion unconditional secure messages. But what you require is the key to be random, to be secret, and of course to be shared between the two of them. And in a sense, cryptography can be thought of as solving two problems. One is, how can the key be exchanged? How can a secret shared key be obtained between Alice and Bob? And once they have it, how can they use it? Now, the second question, how can they use it, is solved by the one-time pad, provided they have a long enough key. Now, when I say long enough, I really mean it. I mean that you need the key to be as long as the message you want to send. It may sound impractical, and it is to some extent, but it gives you such high security that in some contexts, you're willing to pay the price. For instance, this system was used on a red telephone between Washington and Moscow. That's how Khrushchev and Kennedy discussed the situation over the red telephone during the Cold War. And it was fine in those days because only two people needed this security. And the key was physically transported on a magnetic tape by a diplomat who would just take the airplane and put the tape in his diplomatic briefcase and strap around his wrist, and then physically deliver from one place to the other. So if you only need two people to have this high security level, that one-time pad is perfectly usable. But in our society, when anybody may want to communicate in secret with anybody else, it's no longer really a feasible solution. So the one-time pad is perfect, but not practical for most purposes. And the other thing about a one-time pad that is really important to understand is that it's called one-time pad because it should not be reused. Its security was mathematically proven by Claude Shannon, the founder of information theory, in the mid-40s, in the late 40s. So, but Shannon also proved that you cannot do any better. You need a key as long as the message, and you need to be able to use it, and you need to use it only once. If you ever reuse that key to send another message, all security is lost. Not only in theory, even in practice. So if you want to exchange many messages, you need a key which is long enough that you can just chop it in parts and use different segments of the key for different messages. And then, of course, security is guaranteed. But never reuse the same bit of the key more than once. So the question that quantum mechanics can solve here is the use of quantum. So what we're going to use here is very, very simple quantum mechanics. We're going to use polarized photons again, as in the old banknotes. We're going to use the fact that quantum mechanics tells us that it's not possible to distinguish between these four photons, these four polarizations. Even if you receive a photon and you're promised that it's in one of these four polarizations, no apparatus can exist that will tell you which one it is with any reliability. So this is an easy fact to establish from quantum mechanics. And now, so as I said, you cannot distinguish them. So what you're going to, so the first idea that Bennett and I had, the first idea was, well, and this led to the paper called Quantum Cryptography number 2, how to reuse a one-time pad safely. So the idea is that, I just told you one-time pad should never be reused, but the reason it should not be reused is interesting mathematically in itself. It's because if you use a one-time pad to send, to encipher and transmit an actual message, which you want confidential, then what Shannon proved is that an eavesdropper who intercepts this coded message, the ciphertext, but does not know the key, will have no information about the clear text, except for its length and its existence and who's talking to whom, but will have no information otherwise about the clear text itself. However, an eavesdropper who intercepts the ciphertext will obtain information about the key. And that's why you should not reuse it again. Because if you reuse it a second time, then, then the assumption that the key is unknown is no longer valid. Now, because of the first use, some information about the key has leaked, which is fine if you don't reuse it. But if you reuse it the second time, information about the key is known, and that's how it's broken. So the idea we had back in 1982 is that if the eavesdropper, in fact, does not exist or does not intercept the message, well, then no information about the message will leak. Of course, there's no eavesdropper, but no information about the key will leak either. And therefore, you can reuse the key. So the original idea, not very practical yet, but the original idea was that if you encode your message in a quantum system, and here we use two levels of one-time pads, and I will not explain in detail because it's only of historical interest, and I think the microphone is not working well. So if we use the two levels of one-time pad encryption, and we encode the message in the form of a in the form of a quantum signal, then what we can get is that so if Alice sends the encoded message to Bob, any attempt by an eavesdropper to measure it will create a disturbance, because you cannot measure quantum information without disturbing it. So that what Bob will receive will be different from what Alice had sent. And by using appropriate schemes, it's possible for Bob, and in this case, Alice and Bob already they share a very long one-time pad. In fact, longer than the classical case. However, this long one-time pad will allow Bob to know that there's been disturbance. And if there is, and if there has been disturbance, then they will know that the key is no longer secure, and they will not reuse it. On the other hand, if they detect no disturbance, then the key is secure and they can keep reusing it. So as long as there is no eavesdropping, it's fine to reuse your one-time pad. But in the classical case, there is no way to know there has been no eavesdropping, whereas here there is. So what quantum mechanics gives us really is a channel in which it's impossible in principle for an eavesdropper to do passive eavesdropping. It's not possible to just take down the information and then try to analyze it later. Any attempt at eavesdropping leaves a trace, and that trace can be detected. And therefore, just to repeat, if there's been no eavesdropping, you can reuse a one-time pad as long, again and again and again. And whenever eavesdropping is detected, then you need to throw away this one-time pad and need another one. So what this gives you is the possibility to reuse a one-time pad indefinitely long, as long as there's no eavesdropping, going against the theorem of Shannon, which of course is mathematically impeccable, that you should not reuse a one-time pad. It was not practical. So the reason why this idea was not practical is that it required the quantum information, namely these polarized photons, to go from Alice to Bob. Forget eavesdropper for the moment. Let's say there's no eavesdropping. But so it required a signal that Alice would create and send to Bob to arrive with high reliability. We could tolerate some errors by having an error correction code, but not too much, because too much error correction would be useful for the eavesdropper. So if a significant proportion of the photons sent by Alice would not reach Bob, which is what happens in real life on optical fiber, for instance, over long distances, well then, Bob would not be able to decode it even if there's no eavesdropper. So the main disadvantage of this idea was that it could not tolerate significant loss in the quantum channel. And that's when we had, Charlie Bennett and we had, I think, the most significant idea, which was to use this idea, but not to send the actual message, just to send a random bit string. So far what I've shown you is these states cannot be distinguished reliably, and therefore any eavesdropping attempt will create errors that can be detected. That's what I told you so far. But now the next idea was to use this quantum channel not to send a message, but to send a random key. And once the key has been obtained, then it can be used as a classical one-time pad to send a message. So that we would use the quantum channel literally only to solve the key distribution problem. At the end of the quantum part of the protocol, Alice and Bob would have a key as long as they want, purely random, secret, shared, and then they would revert to a completely classical approach to encipher their message using that key with a one-time pad. So as long as the key is indeed secret, the message is secure. And if it's not secret, then enough errors will have been created that they will know about it. So now in the new version, Alice and Bob have no secret initially, and they will create a secret, and I'll come back to that in a minute. So Alice and Bob will create a secret using this quantum channel in a way that the eavesdropper, if he's not there, will not disturb, and the secret will be obtained. But if there is too much eavesdropping, that will create enough disturbance that Alice and Bob would be alerted. They might not be able to get the secret. They might fail at getting a secret. They might fail at communicating altogether. But what the eavesdropper will not be able to do is fool them into thinking that they have a secret key when they don't have one. So the worst the eavesdropper can do is he can prevent them from communicating. But he cannot fool them into trying to communicate and then having the transmission being eavesdropped on. So confidentiality is assured. Communication is not assured, but confidentiality is assured. And this is the idea that came to be known as BB84, because it was published in the proceedings of this conference, not very far from here, although it's not all that close either, but in Bangalore in 1984. So this BB84 paper, here, let me show you the first page of it. And in particular, so this paper is the first time that a protocol was given in print. And here is so also the first time that the words quantum key distribution came out. And the protocol in that proceedings was described by this picture. It's an interesting artifact. You can see that in those days, photons were drawn by hand. And so let me take a few minutes to tell you what the protocol is for those who don't know. To understand how the protocol works, we come back to these four polarizations. Again, no measurement can distinguish all four kinds, so an eavesdropper who would try to intercept the quantum communication would leave a trace. However, what is possible is to distinguish with arbitrary precision between two orthogonal polarizations. So between horizontal and vertical, you can use this apparatus with a calcite crystal that will separate between horizontal and vertical polarization reliably, and then use single photon detectors. So it is possible to distinguish between these two polarizations reliably. Similarly, the same apparatus, if you just turn the crystal, will distinguish between plus and minus 45 degrees. So you can distinguish between these two or between these two, but you have to choose which measurement you make. If you do this measurement, that will randomize those two, and vice versa. So the idea is to use these four polarizations, giving two different codings for zeros and ones. We encode 0, we call this the rectilinear basis, in which 0 is horizontal and 1 is vertical, and the diagonal basis, in which 0 is plus 45 and 1 is minus 45 degrees. And this is known to everyone. There's no secret here. And now, when Alice wants to establish a secret key with Bob, again, Alice and Bob have no secret initially in common. So what Alice will do, she will choose on her own, without telling Bob, she will choose a random sequence of bases, of coding bases, rectilinear or diagonal, she will also choose a random sequence of bits. Just look at the bits for the moment. And now for each pair of a bit and a basis, that gives rise to one polarization. So in the rectilinear basis, I told you that we're going in a rectilinear basis, we encode 1 with a vertical photon. So here, since Alice in the first slot chose rectilinear basis and bit 1, that gives a vertical photon, and so on. So these choices really amount into a sequence of polarized photons in one of these 4 polarizations at random. And now Alice sends all of those to Bob over a quantum channel. Bob does not know which measurements to make. Bob has no secret in common with Alice yet. So Bob doesn't know which measurement to make, so he's going to choose random measurements. He's going to choose random bases to make the measurements, independently from Alice. So that's the decoding or the measurement basis. And he will get results of the measurements. So for instance, if Bob chooses the same basis as Alice, then he gets the same answer. If there's no eavesdropping, and if all apparatus is perfect, which is not in practice. But we'll come back to that afterwards. On the other hand, if Bob chooses the wrong measurement basis, then he gets a random answer, uncorrelated with Alice's bit. Because if you measure, let's say in the rectilinear basis, if you measure a diagonal photon, you get randomly horizontal or vertical, independently of which diagonal it was. So at that point, about 3/4 of these bits are correct, because about half the bases were chosen correctly, and then it gives the correct bit. And the other half basis was chosen at random incorrectly, and gives a random answer, which half the time is the same as Alice's. So in terms of, not in terms of photons, but in terms of bits, 3/4 are correct. But that's not good enough. There's nothing you can do with a 3/4 correct random bit string. So that's when, so at that point, that the quantum transmission is finished. All the quantum part of the protocol is finished. Now we're going to use a back channel, but purely classical. Now Bob talks to Alice classically over a normal classical line. Now this line is insecure in the sense that the eavesdropper can listen to it with no restriction. There's no security in terms of eavesdropping on this line. So what Bob tells Alice which basis he used, but it doesn't tell her the result of the measurements, only which bases were used. And now Alice tells him back, so this should be double arrows actually. Alice tells him back which of these bases were chosen correctly. So whenever Alice tells Bob that he chose a wrong basis, then Bob just drops the bit. This is now irrelevant. So we only keep the bits that correspond to measurements made at the correct basis. And we call that a sifted key. And of course, Alice remembers which of the bases were correct, so Alice also only keeps the corresponding bits. And these bit strings are the same between Alice and Bob if there's no eavesdropping and no errors due to imperfect apparatus. Now, in practice, of course, there will be errors. So at this point, Alice and Bob have to discuss the situation still classically, figure out an error rate, and as a function of the error rate, estimate the amount of eavesdropping that's been going on, and decide to proceed or not from there. But these are all classical steps that are entirely under control, and I don't really have time to give detail. Now let's see what happens if there is an eavesdropper. Well, an eavesdropper could do all kinds of things. The eavesdropper could, the most obvious thing that the eavesdropper could do is to do the same thing as Bob. And you might wonder, why does Bob have an advantage over the eavesdropper? After all, initially, Alice and Bob had no secret in common. The eavesdropper is no better or no worse than Bob, apparently. Well, the reason is that if the eavesdropper tries to make measurements, if she tries to do the same thing as Bob, she will choose random measurements, and sometimes she will choose the correct measurement, and what she does in any case, whenever she measures something, she resends to Bob the result of her measurement. So if she makes the correct measurement, she gets the correct answer, she resends it to Bob, and Bob will not notice a difference. There's no error here. On the other hand, if she makes the wrong measurement, then she will send to Bob something different from what Alice had sent. And then when Bob measures it, that could create an error. So what will happen here, for instance, in this case, See, Alice had sent a plus 45-degree photon. The eavesdropper measured rectilinearly, got horizontal, sent a horizontal to Bob, and when Bob made the correct measurement, because it was horizontal and the measurement was diagonal, he could just have gotten minus 45, and that's an error. So what will happen if you think of it for a minute, you will see that about 1/4 of the bits will be in error because of this. And so in this case, the shifted key has some errors, here more than on average, but on average, 1/4 of the bits will be in error. So the idea is that at this point, as I said before, Alice and Bob will discuss the situation classically to decide what to do. And they will estimate from the error rate, they will estimate an error rate by kind of a quality control sampling. From the error rate, they will estimate the amount of eavesdropping that may have taken place. And from this, they will estimate how much information the eavesdropper might have obtained. So at this point, just by looking at the error rate between Alice and Bob's sifted key, by looking at the error rate, they will be able to estimate how much information the eavesdropper could have obtained, not only by this possible attack, but by any possible eavesdropping strategy allowed by quantum physics. And that's where it gets hard mathematically, because now we have to analyze all possible eavesdropping strategies that would give rise to a given error rate. And in fact, it took 10 years before we could prove formally how much information can have leaked as a function of the error rate. But as I said, this is under control. And once they have done that, then Alice and Bob know how much information the eavesdropper might have in the worst case. And then they use another classical protocol known as privacy amplification, which I will not explain either, that removes that information from the eavesdropper, even though they don't know where it is. They only have an estimate on how much information, but they don't know where it is. Still, it's fairly easy classically to remove that information by shrinking the key. So now they have a shorter key, but on which they can prove mathematically that the eavesdropper, except with exponentially small probability, that the eavesdropper only has an exponentially small number of 1 bit of information about that key. So that's what we mean by unconditionally secure. And only then, if there is anything left, because there has been too much eavesdropping, then the final key is of length 0. But if there's not been too much eavesdropping, then they end up with a key which will be long enough that now they can use it as a one-time pad to send the actual message. OK. One last thing about this is that what I explained, in fact, is in fact, I'm sorry to say, entirely insecure. There is a major bug, major error in what I just told you, which is that in what I told you, nothing prevents. So what I told you is that if Alice and Bob, they use this protocol where this is classical and quantum communication to end up with a final key. What I told you is that any eavesdropper who would try to measure quantum information would create errors. And by creating errors, it will create errors in the key. And that will be detected. And that's fine. However, what I did not cover in what I said so far is the possibility for the eavesdropper to play the entire game with Alice and independently play the game with Bob. And if really Alice and Bob have no secret in common, the real goal would be that Alice and Bob have no secret initially. They've never even talked to each other. Well, then how could they possibly know they're talking to the right person? So there's nothing that prevents Eve, the eavesdropper, from pretending to Alice that she's Bob and pretending to Bob that she's Alice. And at the end of the day, the eavesdropper will have a secret key with Alice and a different secret key with Bob. And in fact, if the eavesdropper plays the cards right, she can even steer the protocol. So in this case, Alice and Bob don't have a secret key in common. They might discover that later. But in fact, if she plays the game in a slightly more clever way, she can steer the final key to be the same between Alice and Bob. So now Alice and Bob have the same secret key, but in fact, it's perfectly known to the eavesdropper. And there's no way they can tell. So this looks pretty bad. And then a miracle happens. The miracle is that so Shannon proved, as I told you earlier, Shannon proved that in order to get unconditional confidentiality, you need a secret key as long as the message you want to send. It's a theorem in classical physics. With a shorter key, or to be more precise, you need as much entropy of secrecy as the entropy of the message you want to send. You cannot do it better with less secret. That's for confidentiality, for the confidential transmission of information. However, it's not the case that you need such a long key for unconditionally secure authentication. So secrecy requires very long keys, but not authentication. There are purely classical protocols that allow Alice and Bob to authenticate messages they send each other. And they can get unconditionally secure authentication, meaning that an eavesdropper, not only an eavesdropper, but a tamperer, someone who comes in between and sends, not only listens to the messages, but injects false messages, will be detected. So if you have a reasonably short secret key, you can make sure that very long messages that you send each other are authentic. And that prevents the eavesdropper from playing the man-in-the-middle attack that I just described. And therefore, if Alice and Bob initially share a short secret key, not all that short, but still a shorter secret key, then they can use that through the BB84 protocol to authenticate all the classical messages. So the security on the quantum message is given by physics. Security on the classical messages, there's none in terms of eavesdropping, but full security in terms of tampering. And that's provided by authentication. This authentication requires a short secret key. And at the end of the protocol, if all goes well, Alice and Bob have obtained a much, much, much longer secret. And this much longer secret, they can keep some of it for authentication next time around and use the rest for confidentiality. So BB84 is a key expansion scheme. It does not create a key out of nothing. It creates a long key out of a short one. And that, to come back to what I said earlier in the talk, is the thing which is classically impossible. To be information theoretically able to increase the entropy of secrecy is something we can prove is not possible in the classical world. And yet, that's what quantum mechanics gives us. To go from a short secret, it has to be there already, so you need a seed. It's kind of unfortunate. We wish it were not the case, but that's life. So you need a short secret as a seed, but from that you can get an arbitrarily long secret, which is whose confidentiality is unconditional. And then you can use it as a one-time pad to send an actual message. All right, so that's a theory. How about practice? Can you actually do that? If you want to implement the theory that I just described, probably what you're going to end up with is not exactly the ideal protocol. You'll have to do all kinds of things which are not as prescribed by the instructions, if I should say. Nevertheless, Bennett and I, about 5 years after we invented the protocol and nobody paying attention, I mean, this initially was not taken seriously by anyone for many, many years. So at some point, we decided to do a proof of concept. Now, we are theoreticians, so we hired 3 students, 3 other theoreticians. So all of us 5 theoreticians together had absolutely no idea how to handle a real apparatus. But nevertheless, we were able to design and build this prototype in 1989. It came out in Scientific American in 92. But this worked in 1989. We were able to do the first actual secret transmission guaranteed by quantum mechanics. I should say, just for the record, that this was provably secure as long as the eavesdropper is deaf, cannot hear a thing, because the biggest part is the power supply. The power supply was used to turn polarizations under control of the computer by applying a 1,000-volt on device, some kind of crystal, nonlinear crystal. When you put in some voltage, it kind of tweaks and rotate polarization. And you all know that power supplies make a lot of noise. So in fact, we could hear the photons go through by listening to power supply, and zeros and ones did not make the same noise. So it was perfectly secure as long as the eavesdropper is deaf, as I said. It was a complete of a joke of an apparatus, and this was taken seriously, whereas the theory, which was perfect, was not taken seriously. It's kind of strange. But after this, some serious experimentalists entered the game and began building versions of this idea which were serious. This was a joke. So throughout the next 10 or 15 years, more and more elaborate prototypes were built, not by us, by real experimentalists. And today, in fact, you can even go on the internet. For instance, ID Quantique. ID Quantique markets quantum cryptographic apparatus. So now you can just go to the internet, buy this thing, buy two of them, one for Alice, one for Bob. You link them by fiber optics over 100 kilometers, and it self-calibrates. It works by itself. It's called plug and play. You don't need to be an engineer to make it work. So quantum cryptography has entered the real world, although it's not widely used yet. And it's only one of several companies that market this equipment. And the microphone is not working anymore. In fact, at some point, the MIT Technology Review magazine had an issue on 10 emerging technologies that will change the world, in which this device, or rather its predecessor, which is built by this man, Nicolas Gisin, and his group, was one of these emerging technologies that will change the world. Okay. What I explained so far is quantum cryptography between two endpoints, somewhat like the good old red telephone in the Cold War. Of course, if you want this technology to become used in real life, you want it to be able to be in a kind of a network situation. You don't want to just be a point-to-point solution. So it is possible also to do quantum cryptography in networks. It's not yet fully developed, but there was a major conference in Vienna a few years ago, which was the end point of a European grant, in which many different universities and research centers had built different technologies, and they had all woven them together. And so during this demonstration, you had many links across Austria in a network like this with significant distances sometimes, using different technologies of quantum cryptography, because I explained it to you in terms of photon polarization, but you can also use phase, you can use entanglement, you can use all kinds of ways. You can use fiber optics or line of sight. And so there were various different technologies used, and all interwoven together into a network that could allow two sides that are not linked directly to exchange confidential messages. Now, this is not a perfect solution because it required trust in each of the intermediary nodes. But as long as all the nodes are trusted, you could have unconditional security between any two nodes. Experimentally, again, there is a few years ago, there was an experiment done in a line-of-sight scenario, meaning there is no fiber optics between Alice and Bob. Alice is on top of a mountain. This is the Canary Island. And in La Palma, one of the islands, Alice was on top of a mountain, and she actually sent single photons over to Bob, who was 144 kilometers away on a different island of the Canary Islands. And Bob was able, with his telescope, to catch Alice's photons and distinguish them from all the pollution coming from the sun. Lots more photons. And analyze them. And Alice and Bob were able to establish a secret key over that distance without any fiber optics. Just line of sight. Quite remarkable technology. And the next thing to do, but this is still kind of point to point. But the next thing that we want to do is to go by satellite, in which Alice and Bob can be now anywhere on Earth, any distance, and they can use a space station or a satellite to mediate their quantum transmission. Now, this has been done. This is not done yet, but it's not science fiction. It's not science fiction because the plan, all the maps, how to do it is perfectly under control. We know that it's technologically possible because the air disturbance in this experiment, over 144 kilometer horizontal, is less, much less, than the air disturbance up to a satellite. It's much further away, but the air is rarefied, of course. So the amount of disturbance here is much, much less, despite a much greater distance than here. So we know that technologically it's feasible. Of course, the beam will spread more, so we have to worry about other things. But still, there is a specific project under study at the European Space Agency to do that. We're just hoping that it will go through. Now it's political. It's no longer scientific. And there's also one in Canada is also working on its own. We have also plans for doing that with the Canadian Space Agency. There are several groups, the most vocal of which being in Sweden, called quantum hackers. And quantum hackers, their business is to poke holes not in the protocol, which is proven unconditionally secure. If they could break the protocol, theoretically speaking, then they would get a Nobel Prize because they would have proven quantum mechanics is wrong. No, of course not. What they do is to go around and poke holes in implementations. Because again, if you want to implement the idea, you will not do it exactly right. And sometimes it's possible to exploit the ways in which the actual implementation deviates from the correct protocol. So the most visible quantum hacker is Vidya-mitra, quite a character really. And Makarov, what he likes to do is to go from town to town with his quantum hacking briefcase. Now this briefcase, which I've seen in real life, is about this big. So it's small enough that he can bring it in the airplane with him. And this quantum hacking briefcase contains all you need to break just about any prototype that's been built so far. Maybe all of them, but I don't want to be so. And if you go to their website, here they have an example. In a website, fairly recently, in July of this year, they did a full eavesdropping experiment in which they extracted the full secret key that was exchanged by a commercial prototype. No, not prototypes, commercial product, right? So they took a commercial product, and they were able to extract the entire secret key exchange between Alice and Bob, which was, of course, not a secret key after all, in a way that left no trace. It was completely unnoticed. Again, they have not broken the protocol. They've broken the implementation. But it's really interesting the way they do that. They have all kinds of ideas, all kinds of different ways of defeating the protocols. No, sorry, the implementations. So who will win after all? Well, I guess the jury is still out. We don't know who's going to win. We have a theoretical protocol, yes, which is invulnerable, provably so, unless quantum mechanics is wrong. On the one hand, we have faulty implementations on the other hand. Now, is it possible, and this comes back to something was said yesterday in this room, is it conceivable at some point that we could build an apparatus that, without being perfect, because that doesn't exist, would be close enough to the theoretical protocol to be provably invulnerable to any possible attacks, even those that we have not thought of yet. After all, this is the case for the theoretical protocol. It's provably secure against all possible measurements allowed by quantum mechanics. So could we hope at some point to build an apparatus that, without being perfect, would nevertheless be provably secure against all possible eavesdropping attacks? And I see someone who says no, and the answer is yes. The answer is yes, but by using something very different from what I described, this BB84 protocol. The answer lies upon entanglement. So in 1991, 20 years ago, Arthur Eckert wrote a very influential paper where he proposed to do quantum cryptography using different principles from BB84. In this case, using entanglement and Bell's theorem, and violations of Bell's theorem. And in his original paper, in fact, offered no security whatsoever beyond that of BB84. There was nothing. I mean, it was using different principles, but it was not offering more security in any ways. However, in the years that came afterwards, it came to be realized that if we use entanglement, if we use violations of Bell inequality to test for eavesdropping, then it is possible in principle, and this is completely beyond current technology to do it. But what is possible at the moment as a theory, we have a complete design of of an apparatus, which we cannot build, again, with current technology. But this apparatus, if we could build it, would offer a security which is based only on the assumption, which might be questionable today, but only on the assumption that no information can travel faster than the speed of light. And Alice and Bob, by using this apparatus, as long as they can feed in their own randomness, so they cannot trust the apparatus. In fact, this apparatus could even be manufactured by the eavesdropper herself. Right? So what the theory says is that once we have these apparatuses, even if they're built by the enemy, as long as Alice and Bob can feed into their apparatus their own randomness, and as long as their own laboratory or space is sealed from the outside, because of course, if the apparatus is built by the eavesdropper, nothing prevents the eavesdropper from having a bug in it that just beams out the key at the end, outside of Alice's lab. So we need to assume that the space of Alice and Bob is inviolable. So these are big assumptions. But once we believe that, and that we have true randomness, then Alice and Bob, by looking at what comes out of the apparatus, which they don't trust again, but just by looking at what comes out of the apparatus and comparing it with the randomness that they put in, they can do statistical tests that would prove that the final key is unconditionally secure, or maybe the result is that they don't get a key. But if the apparatus is working properly, and if there's no eavesdropping, then they will get a key, and they can make sure that the key is secure. Again, regardless of how the apparatus actually works. That's the beauty of it. So they don't need to know how, they don't need to trust in any way the innards of the apparatus. Just by looking at the input of random bits and the output from the apparatus and studying that classically on their own, they can make sure that the key is secure. Again, under the only assumption that the speed of light is the limit for information transmission. It's really, really remarkable. Really, I would take only 1 minute to tell you that what I discussed so far is confidentiality of information transmission. Now, for those of you who know classical cryptography, cryptography goes a lot beyond just sending secret information. There are all kinds of things you can do with cryptography. And a very natural question is, all of these things you can do with classical cryptography, can you do them better with quantum mechanics? And there are all kinds of examples. Sometimes the answer is yes, you can do better. Sometimes you can do perfectly. Sometimes you can do just a little bit better. Sometimes you cannot do any better. Coin flipping is an example. In the early BB-84, this is the BB-84 paper, we had quantum key distribution, but also quantum coin tossing. This is an old idea. So we can use quantum mechanics to toss coins better than classically possible. Oblivious transfer is the old idea of Wiesner, which we can do better with quantum mechanics than with classical physics. And all kinds of other things in classical cryptography that you can do better using quantum approach. All right, so I'll stop here with conclusion that quantum cryptography is unconditionally secure, at least in principle. It's feasible with current technology, although maybe not in ways that are unconditionally secure. So these two lines might not go well together. Commercially available, well, maybe you should wait again a little bit. But it certainly is an active research area. And the main reason to work in quantum crypto is that it's fun. All right, thank you for your attention.